Today we are going to present our project InstaDiagnose. Accessing timely healthcare in Canada is a growing challenge. According to the report, over 50% of people have to wait more than 2 days to see a family doctor, and 20% have to wait more than weeks. These delays could lead to a worsening of the patient condition. So our goal is to create a virtual family doctor tool for primary care. Users can just describe their symptoms and then receive the immediate, reliable disease suggestions. This empowers individuals to take proactive steps toward care before seeing a doctor, while also reducing the burden on healthcare services. For the dataset, we collected symptom description dataset, which contains sentences describing symptoms paired with their corresponding disease. This dataset is used for evaluating our model's performance. We also utilize a medical database for RAG, which contains over 400 diseases and their associated symptoms. This database is used for enhance our model's accuracy.
We define 3 main tasks for our model. First, diagnosing potential diseases. Second, comparing previous and new diagnoses. And third, gathering additional information from the patient when the model is uncertain in its results. We started with a single agent for all 3 tasks, but we found it struggling with generating follow-up questions. To adjust this, we defined a refined model with 3 specialized agents: a diagnosis agent, a comparison agent, and an inquiry agent. So in this new model, the patient described their symptoms, and a diagnosis agent generated a list of 4 potential diseases based on the patient and doctor conversation history. If there is a previous disease list, the comparison agent calculates the similarity score, which can reflect the model certainty. This score, along with diagnosis list and chat history, is sent to the inquiry agent. If the model is uncertain, the inquiry agent asks specific follow-up questions. Otherwise, it summarizes and presents the final diagnosis, which are enhanced with RAG.
Okay, now let's start a conversation with our model to see its performance. Well, for here, I use my actual disease, COVID-19. I began by describing my symptoms, fever and sore throat. The system analyzes and asks me more general questions first. For example, have you been in close contact with anyone who has similar symptoms? I answer these all questions, and the system refining its understanding by asking more specific questions. For example, have you noticed any loss of taste or smell? I understand all of that again. Finally, I feel I have already provided enough information, so I want to stop this conversation by just telling the system I have no more information. And in the end, the system provided me 4 possible illnesses, and in this case, it has successfully identified COVID-19, which ranked number 2, but well, actually the top one, the influenza and COVID-19 are both viral infections, so we do think our model did a really good job. So you may have a question, how did we choose our best model? We used 2 metrics. First, top 4 accuracy, which check whether the correct diagnosis in the top 4 predictions. Second, top 4 weighted score, which assign more scores for higher rank pretension. And you can see the table below. And after that, we compared 5 different models, and we found 3 agents models with RAGs has the best performance, which achieve an accuracy over 88% and have a really high weighted scores, which is 175. And in the end, we also evaluate our best model in real-world scenario by inviting 10 users to use our system and consult with a real doctor. And here's our result. Given the small difference in weighted scores and they have the same accuracy, our systems provide us a really strong potential and competitive performance.
Start with the conclusion. The results make sense as we see complex model performs the best, which means our improvement is meaningful, and outputs are approved by the doctor. From the quantity result, we notice that more agents break down tasks, so each can handle a simpler work, and this makes a big improvement. Also, applying RAG performs better, but in this case, a well-chosen dataset and a good cleaning process are required for detailed solutions while optimizing the restrictions. And doctor criteria is important that can affect labeling. For example, this prediction is different with the actual disease, but they mean the same thing. So whether they match depends on the doctor's knowledge. Based on the result quality, we found that keeping prompt simple can reduce noise that may cause unexpected output. So prompt engineering is necessary, and we need to consider trade-offs to have smooth diagnosis process. Based on our learning, limitations exist since only descriptions are not sufficient. For example, the skin diseases require more in-person diagnosis for high accuracy. And we can add image recognition in the future. We still need more prompt engineering to improve user interaction and more user study for testing and adjustment. And here's our acknowledgement. I also want to thank for our Professor Jonathan and the help of TA Solomon. Yeah, thank you.
Thank you.